is going to be the last day that's exclusively on hashing. I just want to correct the lemma that I stated, I guess, at the end of class, or at some point in class last time. It was related to cuckoo hashing. Well, before I do that, so today, what are we going to talk about today? So we're going to finish linear probing. And I'm going to show you how you would argue about it with 5 whys independence. It's almost the same proof as 7 whys. There's just one trick that you have to observe. I'm going to talk about approximate membership. So this is Bloom filters. I'm going to talk about cuckoo hashing. Bloomier filters, which solve a different problem than Bloom filters. Well, generalization. I'll say a little bit about the power of 2 choices. And 6 is, well, I might say some other stuff. Okay, so. Okay, so before we start with the 5 whys, I just want to very quickly recap the 7 whys and tell you what the lemma was that I should have said. So the lemma that I should have said, so let's recap. This is for linear probing. Okay. We have an array, so we hash to an array of size m. And I think I assumed that m was, at least, let's say, 2n. Okay. And we said Li, so let's say I is an interval of array locations. And then I said Li is the number of j in the set S. S is the set of things that live in, the keys that live in our data structure, such that h of j is in I. It's the size of that set. Okay. And I gave a definition. I said that I is full, okay, if L of I is at least the size of I. So then I stated some lemma about the number of probes, relating the number of probes that we do when inserting x to full intervals. Here's a lemma that I should have stated, which I sent by email. By the way, is everyone here on the class mailing list? Is there any? Please raise your hand if you did not receive an email about class-related things. Raise your hand. So okay, I guess everybody's on it. Okay, so if someone's too shy to raise their hand, you can go to the class website, and there's a link to sign yourself up. Okay, so the lemma that I should have said is if inserting x takes k probes, then h of x is contained in at least k full intervals, each of length at least k. Okay. And the proof of that is you draw the array. H of x goes somewhere. Okay. And some window about this is taken, is occupied by items. Well, I'm using, that's just, some window is taken up by items, and then there's a free spot, and then also going backwards, some window is taken up by items. Okay. And the point is that, and this is empty. And the point is that this interval here, this interval here, it lands somewhere. So h of x will eventually go there. This interval here, including the item x itself, is a full interval. Okay. So if you just take, so any prefix interval is also full. So if you just take the k different prefix intervals that start with here, so take this one, take that one, et cetera, those are all full intervals. Yeah?
Maybe of length less than k if the interval starts only 1 to the left.
Well, you know, the thing is, you know that this here has length k, because we're making k probes. So what you can do is start here and go k to the right. Or I mean, well, start.
You don't need like at least.
Oh, it doesn't. Oh, yeah. Sorry. This interval doesn't have to be size exactly k. It can be size larger than k. So start from the beginning and just go all the way to h of x, and then more if you need to make it length k. Do you have a question?
I think in a lemma you don't need the length at least k coefficient. Otherwise it's
Why is it false?
everything hashes to h of x. So
Everything hashes here.
you don't get k things. So then the lengths won't be at least k.
No, but then this interval would be of length. This interval would be full.
Yeah.
Oh, I see what you mean. Oh, yeah. Okay, fine.
The length at least k.
Okay. Yeah. Okay. Good. So, man, so this lemma is really causing me a lot of problems. Okay, I see. Okay. And okay, so what was the purpose of this lemma? The purpose of this lemma was we wanted to say that the number of probes to insert x is at most the number of full intervals containing x. Okay. So this inequality was the whole point of that lemma. And the reason this is true is, in particular, like the k different full intervals that appear in this lemma are a subset of all the full intervals containing x, containing h of x. Okay. And then we carried on from there. And then we said this thing here is at most the sum over all k. Well, it's equal to the sum over all k from 1 to infinity, the sum over all intervals of size k such that h of x is in I, of the probability that I is full. And this is at most the sum over k, the sum over the same kind of I, h of x is contained in I, of the probability that L of I minus the expectation of L of I is at least the expectation of L of I. Right? Because the expectation of L of I is the size of I over 2, whereas if it's full, we know that at least I things landed there. So it's at least I over 2 bigger than its expectation. And then we use the moment method. We can raise both sides to some power. We raise it to the 6th power. Yeah?
So how can you say in the summation that mod I is k?
I'm sorry, say it again?
Why are you counting only intervals of length k?
I'm counting all intervals. K is a parameter.
Oh, right.
So I'm counting all intervals.
Okay.
Yeah. And then this thing is at most sum over k. There are k intervals of length k that contain h of x. So k times 1 over, so this is I over 2. So this is k over 2 to the 6th times the expectation of this thing, Li minus expectation of Li to the 6th. Okay? So I don't want to say much about how to bound this thing. I mean, well, I want to say something, but I'm not going to actually do the computation. But I'll give you, I guess, a useful trick that lets you easily compute those things. And then I'll leave it to you to execute the trick if you really want to see the final value. Okay. So what is this random variable Li? Okay. So we can define some indicator random variables. So define x1 up to xn, where xi is equal to 1 if h of I is contained in this capital I, and 0 otherwise. Okay, then that implies that L of I is just the sum I and S of x of I. Okay. So now we're looking at a deviation from the expectation. So we want to bound the expectation of we want to bound, the expectation of xi minus the sum over I xi, expectation sum over I xi to the sixth. Right? That's what's over there. Okay, so I want to show you a trick to show you how to make this thing somewhat easier to manage. Okay, so trick for such situations is what I'll call symmetrization. Okay. So what's that trick? So I'm gonna make a claim, which I'm not going to justify. You can look it up if you want. So fact. This is known as Minkowski's inequality. Is that if you look at define for a random variable. So x is a random variable. Define for a random variable x. The p norm of x is the expectation of the absolute value of x to the p to the 1 over p. Okay. This is a norm. It obeys the things you usually expect, like the norm of ax, the norm of a scalar times x is the scalar times the norm of x. It satisfies triangle inequality, etc. So we really want to bound. Oh, and then one other fact that I want to state is called Jensen's inequality. And it says if a function is convex, then f of the expectation of x is at most the expectation of f of x. Oh, this is a norm, I should say, for p at least 1. So the trick that makes computing things like this a little bit easier is, this is the same thing as the 6th norm raised to the 6th power. So let's just bound the 6th norm. And then whatever answer you get at the end, you'll raise it to the 6th power. So you'll say, look, so I have the sum over I xi minus the expectation of sum over I xi. Okay. And you might as well imagine that, so this is just a number. This expectation is just a number. So you might as well imagine that these xi's inside this expectation are independent copies of the actual xi's. So xi prime is a random variable that's independent of xi, but is distributed exactly the same way. So you get the same thing. Right? This is the same number. And then, you could, let's write this suggestively as, I'm just rewriting where the x is. So this is the expectation of, over the x primes now, of sum over I xi minus xi prime. And raising something to the 6th power is a convex function. Or in general, taking the absolute value and raising to the p for p at least 1 is a convex function. So I can pull this expectation outside. So this is the 6th norm over this random variable, but this is at most the 6th norm over both random variables. Okay. So if this isn't clear, this here means expectation over the x's of expectation over the x primes, sum over I xi minus xi prime to the 6th to the 1 over 6th. But taking something and raising it to the 6th power is a convex function. So I can pull this expectation outside. This here can go outside. And it only gets bigger. That's Jensen's inequality. So that's what I did here. So this randomness, this norm is over both x and x prime, are both random. And now these are independent symmetric random variables. So this is exactly the same distribution as putting in random signs. These are independent random signs. So I should have said this is Jensen. And now I use the fact that the 6th norm is a norm. So this is at most 2 times the sum over I sigma I xi. Okay, so what we've just shown is that the original 6th moment that we wanted to bound is bounded up to this 2 to the 6th power, raise everything to the 6th, and then you get the 6th moment. The 6th moment is at most 2 to the 6th times the 6th moment of this random variable, which is a symmetrized version of the original one. So this is a mean 0 random variable now. All these sigma i's, all these guys here are symmetric random variables. And what's the point of that? So, with the 6th power, and things don't get really that, well, 6th power is already kind of annoying, but especially if you go to really high powers, it gets really annoying. But symmetrization makes things slightly easier because let's look at this now. The expectation, remember, what is xi? Xi I define to be this thing here. So in particular, xi is equal to 1 with probability 1/2. Not 1/2, what am I saying? The size of I over m, which is, let's say, k over 2n. Right? What's the probability you land in an interval? You hash to an interval of length k in an array of size m. It's this. And it's equals 0 otherwise. So let me just call this, number p. Yeah. Yeah.
Where are the expected values exactly in the last 2 months?
So, OK, so this really means this.
Yeah.
This means I took this outside. So it's an expectation over both.
There's an expectation over both on the outside of that.
Yeah, so this thing here is the expectation over x and x prime of that thing to the 6th to the 1 over 6th. This is this. Does that answer your question?
Oh, okay.
So now if you want to bound the expectation of sum over I sigma I xi to the 6th, you'll expand this out and you'll get a sum over I1, I2, up to I6 of the expectation of a bunch of sigma powers, sigma I1, sigma I2, sigma I6, times the expectation of xi1, xi6. OK? And the point here now is, what is the expectation of this thing here? What is this expectation? I claim the expectation has one of two possible values. 0, 1. And when is it 0? When is it 1? That will certainly make it 1, but that's not the only time it will be 1. Yes. Every one of these indices I, so there's I1 up to I6, it should appear, some of these i's might equal each other, right? But if you look at the distinct i's that appear here, each one should appear an even number of times. Okay? So, the situations are all appear twice, or one appears 6 times, one appears 4, and one appears 2 times. I think those are the only situations. Okay? And let's say that they're all the same. One appears 6 times. Then this thing here is just xi to the 6th, which is the same as xi, because xi is only 0 or 1. And so that gives you p. Okay? Or if all of them appear, if there's 3 guys appearing twice each, then you'll get p cubed here. Okay? And then you also have to take into consideration the choices of all these i's. So how many ways are there to choose 3 guys to appear twice each? It's like n cubed times some coefficient. So the bottom line is kind of the dominant term is the case where this is dominated by a case of 3 distinct items. I'm not going to do the computation, but if you actually did it, that's what you would find. 3 distinct items appearing twice each. And that gives, well, there are n cubed choices of those 3 items, or n choose 3 choices. And then you have to take into consideration the permutations that all give the same thing. So there are n cubed choices, and then you get p cubed. That gives O of n cubed p cubed. Okay? And remember now, p has a division by n here. So this is O of k cubed, if you remember what p is. And then if you go back here, you get to divide by k to the 6th. So k cubed over k to the 6th is 1 over k cubed, times k is 1 over k squared, and that sum converges. Okay? So you don't have to use this symmetrization. It's just a useful tool because it lets you kind of reason a little, combinatorially. Like the only monomials that matter are the ones with even powers, and then you can count how many there are, etc. Yeah.
Why do you have to introduce the random signs?
Because I want to just say that if you have an odd power, so you're going to choose some set of 6 indices, and I want to say that, yeah, the only monomials that matter are the ones that have all even terms, all even power. Like every index should appear an even number of times, which already tells you that the number of distinct indices can be at most 3, because each one has to appear at least twice, right? If you had to consider every single monomial, well, there are like n to the 6 choices of I1 up to I6. So you get n to this, naively you get n to the 6th here. You'd have to be like more careful because you'd have to reason about things canceling in various places with the expectation that you're subtracting off. Whereas if you symmetrize, that sort of does that for you, and the counting problem is easier. Does that make sense? You have another question about it, maybe?
I guess it makes sense. I just don't know where it comes from or how.
So in terms of where it comes from, I guess it's just a trick. I mean, but in terms of why it's a useful thing to know, maybe as an exercise, don't symmetrize. Just look at this sum. Go home with this sum and raise it to the 6th power and try and reason about what all the monomials give you. Some will give you positive terms. Some will give you negative terms. You have to argue that there's some cancellation going on, right? Whereas with symmetrization, you don't have to worry about that at all. Everything you're adding up is non-negative, and it sort of automatically counts things the right way. Yeah, it's just a trick. It doesn't come from anywhere other than trickery. OK, where was I? I was up there, I think. OK. OK, so I mean that's basically it for why 7y's independence works, right? So once we conditioned on the fact that I contains h of x, the other 6 random variables involved in a product are still independent. That's so one for x and the other 6 for the other 6 guys. So that's 7y's. So good. So we need to. I claim that 7y's works. I proved that 7y's works. I claim that 5y's works. Okay, that's actually what was in that paper by Pei, and Ružić. So the main trick for them to show that 5y's works is to reason in a more careful way so that you don't suffer this k. Okay? We needed this to be 1 over k cubed so that even when that k canceled something, we had a convergent sum. So that's why we needed the 6th moment. Good. So we need to get rid of that k. And the point is, we can be a little more clever about union bounding over all these length k intervals that contain h of x. And let me just say that, so I might have mentioned this last time, so Pei and Ružić, I think their original paper was 07, but they have a journal version later, says that 5y's works. Oh, and just to make sure we're all on the same page here, what did I actually prove, right? I proved there should be an expectation here. I proved that the expected time it takes to insert the item is a constant. Okay, just so we're all on the same page. So by 5y's works, I mean that even if h is only 5y's independent, the expected time will be a constant. And Petrashku and Thorup, I think I mentioned this last time, 4y's is not sufficient. You can come up with a 4y's independent hash family such that there's a pretty good chance, actually, that the number of probes you'll do is log n as opposed to constant. OK, so what's the Pei argument, Pei-Ružić? Let me give myself some space, actually. So the Pei-Ružić argument is as follows. So we have this array here. Okay, of length m. Let's say that it's a power of 2. We build a perfect binary tree, okay, over the locations in the array. Wow, that's not a power. What am I doing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, good. OK. Yeah, I practiced this in my office, and I was really fast, but now I'm getting slower. OK, so we build a perfect binary tree over this array. And we imagine that every node in this array corresponds to an interval of memory locations, namely everything in its subtree. Okay. Remember, we're trying to eliminate that k there. Basically, we don't want to union bound. We don't want to union bound over k intervals of length k. We want to union bound over a constant number of intervals of length k. That would eliminate that k for us and let us get away with a 4th moment. And the basic idea is this. So call a node dangerous if at least, let's say, 3/4 times 2 to the h. So this is a node at height h, items hash there. So height of node is h. So this is height 0, height 1, height 2, height 3, height 4. So the number of locations there is 2 to the h, and we're saying that it's so yeah, the height is the number of locations is 2 to the h, and we're saying that a large fraction are occupied. And what do we expect? How many people do we expect to hash there? Well, if m is equal to n over 2, we expect a half 2 to the h to map there. So we're a constant factor larger than the expectation, which you can show happens with pretty small probability. Let's say this 2 to the h is roughly k. You can show using like a kth pth moment that this would be like 1 over k to the p, or p over 2 or something. Okay. So now what's the point? The point is, oh, I really shouldn't have erased that sum. So let me just write something up here. So at some point, we had this on the board. The expected number of probes to insert x is at most the sum over all k, the probability that there exists. So that's at most the expectation of the number of full intervals containing h of x. Wait a second. Have I confused myself again? I really... I wanted to say this is at most the probability that there exists a full interval of length k containing h of x. But that would only work out if these things were of different lengths. Yeah. OK, so adjust the lemma yet again. So adjust the lemma to say that, so lemma prime is k probes implies at least k full intervals of containing h of x, each of different length. OK. So by a modification of lemma, you can prove this. And now this thing, I want to argue that to argue whether or not there's a full interval of length k containing h of x, we only need to union bound over a constant number of intervals of length roughly k. Okay. So given I of length k, look at the at least 4 and at most 9 nodes in tree. So let's say spanning I at level h minus 2, where k is in the interval from 2 to the h up to 2 to the h plus 1. Okay, so we have this interval of length k. And I'm saying k is roughly 2 to the h. Look at intervals that are roughly 4 to 8 times smaller. So 4 to 8 times smaller in the tree, so like 2 levels below. And look at the ones that span this thing. And I claim that there are certainly at least 4 because they're 4 times smaller. And there are at most 9 because they contain at least an eighth of the interval, and there might be one left over. Okay. Anyway, they're a constant is the point. So if you want to see an example, look at, for example, this interval, 1, 2, 3, 4, 5, 6, 7, 8. So that would be 2 cubed. Let me go bigger. Okay, good. Yeah, 2 cubed. So let's look at this interval. So we need to look at the nodes that are 2 levels lower that contain, so 8 is in the range from 2 cubed to 2 to the 4th. So h corresponds to 3 here. So we look 2 levels lower and look at which nodes fully contain this thing. So you only need to consider basically these nodes. There are 5 of them. Okay. So that's what I mean over here. So look at the first 4 of these nodes. Okay. And what I want to say is these guys, these guys are completely occupied. And this guy here might not be completely occupied. Okay. But I claim that every guy had to start their hashing from at least here. So every guy started his hashing from at least here. So what do I want to say? So let me call this point A. Everyone in first 4 hashed to A or later. And first 4 contains at least 3 times 2 to the h minus 2 plus 1 items. This is the number of items that hashed somewhere in the first 4, which implies that one of these 4 has L of that interval bigger than 3/4 times 2 to the h minus 2. Namely, it's dangerous. Okay. So now the point is, if we're looking at intervals of length k, there are k of them that contain h of x, but they themselves are contained in an interval of length 2k minus 2. All the intervals of length k containing h of x are contained in an interval of length 2k minus 2. And if you look at all of these intervals and look at, the first 4 that you would consider for the first of the intervals, the first 4 that you consider for the next of the intervals in this kind of spanning argument, kind of the total number of nodes at height h minus 2 that you'll consider is a constant. Right? Are people with me? So that the total number of height h minus 2 nodes used to span these intervals is some constant. Okay. And we know that if one of them is full, one of these constant guys has to be dangerous. So it suffices to just argue that there are no dangerous people in this range. We just need to show that if none of these constant number of people are dangerous, then it means that none of these intervals under consideration can be full. So A?
Everyone in the first 4 hash to A.
This A?
Okay.
Just the beginning. So if there exists a full interval of length k containing h of x, then one of these O of 1 nodes of length theta k, let's say at least k over 8, must be dangerous. That implies that the probability that there exists a full interval of length k containing h of x is at most O of 1 times the probability that some length k over 8 interval is dangerous.
Sorry, could you explain again where the 3/4 comes from? Like for the dangerous definition? Like why was it 3/4?
Oh, it's about to appear. Okay, so the reason we call this dangerous is the number of people you expect to land in this interval of length k. So k is 2 to the h here. The number of people you expect to land there is half of the interval length because m is 2n, n being the number of cells in the array. So we expect a half times 2 to the h to land there. So kind of having much more than that land there, like a multiplicative factor more land there, is sort of an anomaly.
Why not 3/5 or I don't know, anything that's bigger than that?
Yeah, you can crank out an argument that uses any constant factor bigger than a half. You could do that, yeah. So the probability that some length k over 8 guy interval is dangerous let me call this interval I prime. That's equal to the probability. That's at most the probability that the length of I prime minus the expectation of the length of I prime is bigger than. So we're basically a half larger than the expectation. Right. We expect Li prime over 2 people. We expect I prime over 2 people there, but we got 3 I prime over 4, which deviates from the expectation by half the expectation. So again, then you use this is at most. This thing here is the size of I prime over 2. So this is at most 1 over the size of I prime over 2 to the 4th times the expectation of Li prime minus the expectation of Li prime to the 4th. and you argue about this the same way, you'll get something that looks like the length of I prime squared. And remember, this guy here is theta k. So here you're going to get 1 over k squared. OK. So I feel like there must be questions. Oh. Well, OK. Feel free to ask me questions. We have Piazza now, so.
Sorry, what height of h minus 2 nodes is constant? Isn't that 2 to the h minus 2? Why is that constant?
So we have this interval of length k, and we're covering it by intervals that have length roughly k over 4 to k over 8. So the number of these intervals we need is a constant. It's somewhere between 4 and 9 of them. Yeah. And even if you look at all the length k intervals combined that cover h of x, that contain h of x, that's a length 2k minus 2 interval. So it's also spanned by a constant number of length k over 8 people. Yeah.
Don't we still have this sum over k?
Yeah, we do have to sum over k. But we're summing over k of 1 over k squared. So this thing here is going to be, if you calculate it, it's going to be 1 over k squared. So this thing here, so this is 1 over k to the 4th. This is going to be about k squared. If you work it out. Okay. Yeah.
Also,
Yeah.
the reason why we're able to make that inequality is because of the 4y is equal to.
Yes, that's right. So even conditioning, so we're conditioning on the fact that I contains h of x. So conditioned on that, that's like one evaluation of h on some point that we're conditioning on. There's still like 4 more that we can afford, and they'll still all act independently because there are only 5 of them altogether. So yeah. So that's why the original statement by, I think, Mihai Petrashku told me is the reason 5y's works is because when you condition on 1, it's 4y's. That's a very vague, cryptic statement. At that before you actually see any arguments. Okay. So let me say something about other types of hashing, namely approximate membership. Who's seen Bloom filters, by the way? Okay, a decent number of people. Okay, so dictionaries. So I'll quickly review Bloom filters, and then we'll get to bloomier filters. But before we get to bloomier filters, I need to say something about cuckoo hashing. So this is a different problem now. This is the membership problem, or approximate membership. So we have a set S, which is which is in U. Okay. And we need to maintain S. So there could be update. These are the two operations we support. One is update. Update X sets S to be S union X. And then there's query X, which says, is X in S? Yes or no? Okay. So there are no keys there are no values anymore in our hash table. There are only keys. We just want to know is the key in our set or not. And I should say that with dictionaries, so dictionaries are where we have values associated with keys. With dictionaries, we were allowing ourselves to use n words of space. With membership, we want to use less space. We want to use like n bits of space. Remember, a word is like log of u bits. So now we want to get away with, instead of n times log u bits, we want to get away with n bits. OK, so the basic idea, so we'll have, the basic idea is to allow some slack. So we will allow false positives. What I mean by that is if x is an S, the probability that query of x is 1, meaning the query will say, yes, x is in your set. That should be 1. And if x is not an S, the probability that query of x is 1 should be at most a half. OK? So this is some randomized guarantee with a probability of failing. And the data structure that gives you this is extremely simple. So the solution is we make an array Yeah.
So the probability of this failing depends on the data structure itself, or can vary from, like, can the answer change between querying one after the other? Or
Say that again. What do you mean?
So if I wanted to like boost this probability to 1/4,
Yeah.
can I just query twice, or would I have to make two different data structures?
No, if you make the same query twice, you'll get the same answer both times.
Okay. So in order to boost this, I'll have to make 2 copies of the data structure.
Yes, that's right. Good. Oh, yeah, you're answering a question. I was going to ask a question about that. So you already gave me the answer, but I'll get back to you very soon. So the idea is, look, so pretend we know n. Of course, if we're updating, if we're inserting into this data structure, n keeps changing. I don't allow deletions, by the way. I'm just allowing insertions. Pretend we know n. Pretend it's just a static problem. OK, we're given all the items up front. What I'm going to do is, look, I'm going to pick an h that maps my items into this array. And when x comes, I'll set h of x to be 1 for x and s. I just hash it and put a 1 in that bit. This is a bit array. It's not an array of words. It's an array of bits. So I have a question. So this, just so we're on the same page, I'm asking, so if you understood what I said, then this should not be real, you know. Well, OK, question, why is this true with the solution? The first bullet. Yeah. What? Yeah, if x is an S, I set the bit to 1, it's 1. So the query is just going to check. I didn't tell you what query does. Query just checks whether that bit is 1 or not. And if it is 1, it says, yes, it's in there. OK, how about if x is not an S? Why is this the case? It could be set by someone else. So then why is the probability at most a half? Right, so as you said, so the probability, so like let's say x is not an S. So then the probability that query of x equals 1 is the same thing as the probability that there exists some y in S such that h of x is equal to h of y. Right? If there's someone who collides, you'll be fooled. So how do you bound this? If I want to be a little pedantic, what's the next thing I would do? Yeah. Yeah, sum over all the possibilities. So I would use the union bound. The probability that there exists a bad y is the sum over all y's of the probability that y is bad. So this is at most the sum. This is union bound. The sum over y and s, the probability that h of x equals h of y, Okay. Yeah.
Sorry, could the 2-bit space marked by 2 separate keys?
Yeah. If a bit is 1, then there's nothing like. You mean if 2 items both map to the same place?
No, I was saying like we need 2 bits to be set for that to be marked. For the query to be 1, right?
There's 1 bit. You just so the update algorithm. This is update. So update, you just evaluate h of x, and you set not set h of x. You set, let's say this array is a. You set a of h of x to 1. And the query is you just output a of h of x. So maybe I'll say what the query is. So the query is you output a of h of x. And the update is you set a of h of x to 1. Does that answer your question?
Maybe I just misremembered the bloom filters. I thought you said 2 bits, and then that's what gives it the magic of.
Oh, yeah, there are many implementations of bloom filters that are somehow, there are trade-offs and constant factors and things. But yeah, so. I mean, I haven't gotten to the actual bloom filter yet. This is just a bit array for now with a hash function. But OK, so now what's this probability? One by m, yes. And there are n different choices of y, so this is n times 1 over m, which is a half. OK, great. OK, so now going back to the point that you raised, having a false positive probability of a half is not really that great. Whoever is using this data structure will come to me and say, Jelani, I'm willing to have a 0.01% chance of false positives, but not a 50% chance. Okay. So suppose they tell you, we want that x not an S implies probability that query of x equals 1 is at most epsilon. So now what would you do? What's a solution you would? Yeah, which I guess is what you said.
Yeah.
But yeah, okay.
Make n times 1 by epsilon.
1 by epsilon. Okay, I don't. So that works, but you can be. Yeah. Anyone, you were about to say something.
I mean, you can make the bit array bigger.
Oh, make it longer.
That's the same thing.
Yeah, you could do that. So yeah, okay, so good. So yeah, you could make it longer. In particular, you want n over m to be epsilon. You make m be n over epsilon. Okay, you could do that. What else could you do?
Log 1 over epsilon copies.
Yeah, that's another thing you can do. You can take log 1 over epsilon copies. So what you do is you'll have a bit array of length m. M is again 2n. But you'll do it many times. Okay? And the number of times you do it is log of 1 over epsilon. And here you'll have your hash function 1, hash function 2, hash function k, where k is log 1 over epsilon. And when you have an update, you'll update in every single array. And when you have a query, what would you do for a query? Search them all, and then what would your answer be? It's in all of them. Yes, exactly. So the query, you just say, are all of these set to 1? So to be fooled, you'd have to be fooled every single time, which happens with probability 1 over 2 to the k, which is epsilon. So the space here is n times log 1 over epsilon bits. So, and the time is O of log 1 over epsilon. It is possible to get more sophisticated and I think improve this time to a constant, as well as support deletions. Okay, but I'm not going to cover that in class. But this is one thing that's called a Bloom filter, and there's a Bloom filter, and it's due to Bloom in 1970, I think. Okay. So that's Bloom filters for the membership problem. And I want to get to bloomier filters. And I'll tell you what bloomier filters solve. I'll tell you what problem they solve. So with Bloom filters, we're solving the membership problem, where you could imagine for every element in our set, we want to be able to look up a bit associated with that element. And here it's the bit 1. But what if we want to associate an r-bit string with every element in the set? Okay. And bloomier filters let you do that with n times r bits. Okay, so that's the retrieval problem. So note that this doesn't solve it still doesn't solve the dictionary problem. Okay. We never actually store the keys anywhere. Like in Bloom filters, we never stored the keys, right? If you actually ask me at some point, what are the elements that are actually in my set, I can't tell you. But if you give me an element, then I can tell you whether or not it's in the set. Bloomier filters are going to be similar. If you give me an element, I'll be able to tell you the r-bit string associated with that element. But if you ask me, what are the keys in this data structure, I won't be able to report them to you. Because in particular, I'm not even using enough space to hold them all. Right? You need n words of space to hold them, and I'm only using n times r bits. Okay. Yeah?
This means that I might get a bit string that's from a different element, right?
Yeah, so if you give me an element that's, actually so I haven't shown you the construction of bloomier filters, but we'll get it to be such that, first of all, we're going to look at static bloomier filters, the static problem, not the dynamic problem. And we'll get an algorithm that doesn't make errors. So if the element x you give me is actually in the set, I'll give you the correct r-bit string. If the element you give me is not in the set, I might just give you total garbage. I mean, I won't know that I gave you garbage, because I don't know what's in the set. Oh, maybe that's what you meant.
Yeah, you get it.
Oh, I see. Yeah, sorry, yeah. You'll get an arbitrary r-bit string with no guarantee.
Right.
OK, good. So yeah, that is right. OK. So before we do bloomier filters, I want to do cuckoo hashing. So maybe I will spend a little bit of time on Tuesday about power of two choices before we get completely out of hashing. But what do I want to say about cuckoo hashing? So cuckoo hashing. Good. So this will be a solution to the dictionary problem. The dynamic dictionary problem. And this is due to Pei and Rodel, Journal of Algorithms 04. And the idea is to use two hash functions instead of one. Okay. And the power of two choices is going to be just our second example of the power of using two hash functions instead of one hash function, but it's sort of a different, a bit different. But OK. And what's the basic idea? Again, we'll have an array A of length m being like c times n, some constant times n. I'll imagine like 4n or something. Oh, by the way, so just make sure we're all happy with Bloom filters. Remember, at some point we talked about KY's independent hash families. What amount of independence do I need to make Bloom filters work? Each one of those hash functions over there, what independence, what kind of hash family should they come from? 2. Why 2? Yeah, because they're all, whenever I reason about how a set of hash evaluations behave, I only care about 2 at a time. So 2y's independence suffices to say that this is 1 over m. Okay, so we have this array of lengths t times n, and we pick 2 hash functions. G and H, mapping U to M. And let's just imagine that they're actually perfect, totally random hash functions. And I don't remember exactly why it's called cuckoo hashing. It has something to do with, I think there's a bird called a cuckoo bird or something. And like a cuckoo bird steals another cuckoo bird's nest. Something like that. It lays eggs in the other person's nest, in the other bird. Okay, good. So it lays eggs in the other bird's nest. So the idea here is, let's say we want to insert x. So nests here are going to be memory cells. Like, okay, so put x in a of h of g of x. Sorry. So just evaluate g. That tells you an entry, and put x there. But there might be someone else there. If some x prime is there, so let me call this location location j. Then if g of x prime is j, put x prime in h of x prime. Otherwise, if h of x prime was j, put x prime in g of x prime. Okay, so we put x somewhere, and there might be an item already living there. If there is an item living there, it got there because of one of its hash functions. So we'll kick it out and send it to where its other hash function wants it to go. But it might then collide with someone else. And then that person will get kicked out and then move to where their other hash function tells them to go. And there will be like this chain of moving things around. And potentially it could go on forever. But hopefully it doesn't. Hopefully it ends very quickly. And that's cuckoo hashing. OK. Other questions about the insertion algorithm? Yeah.
So when you say it could go on forever, are we going to prove it will never go on forever, or just with high likelihood?
We'll prove that OK, so we'll augment the insertion algorithm. So we'll also say if this goes on for more than 10 log n steps, then rebuild the entire data structure. Okay, so we'll go kicking people out of their place and moving them around. And if this chain of moving things around went on for more than 10 log n steps, we'll say, you know what? I'm not feeling very confident about what's happening here. And I'll just pick a totally new h and g at random. And then I'll make a totally new hash table and then try and reinsert everyone in there. And then that might loop again for more than 10 log n steps at some point. If so, I'll give up again. And I'll keep doing this until it works. I mean, yeah. So, no. Well, you could. But what you can show is that the kind of expected, what we're going to end up showing is that the expected insertion time is a constant. Even if you take into consideration that once in a while we have to rebuild the entire data structure, even with that in consideration, the expected time will still be a constant. Yeah.
Is J equal to Gx, right? And not AFGx.
Yeah. So,
Define J for
oh yeah. J is the location. That's right. So our goal is to show that the expected update time is O of 1. OK? Yeah.
Wait, so does this lie immediately if h of x prime equals g of x prime?
If h of x prime equals g of x prime,
Oh no, it'll kick x back out.
yeah, it will kick x back out. That's right. Yeah. OK. So this is what we plan to show. Yeah, that's a good point. Like, just because there's a cycle doesn't mean we're in trouble. Although if there are 2 cycles, then that's worse for us. But what we're going to end up showing is that the probability of having 2 cycles. If you follow, well, we'll get there when we get there. OK. So this is what we want to show. Before we show this goal, let me just knock out bloomier filters. Okay. Like, how are we going to use bloomier filters? So to get bloomier filters, so actually before I say that, the main tool in the analysis, the main tool, oh, I should have asked this a while ago. Do we have a scribe? OK. Oh. OK, so the main tool in the analysis is the cuckoo graph. OK, what's the cuckoo graph? There are m vertices. It's an undirected graph. There are m vertices and n edges. And for each x in S, draw edge between g of x and h of x. Okay. And that's the cuckoo graph. Sorry, say it again.
Can you have 2 edges between 2 vertices? If you have, say,
Oh, like parallel edges? Yeah, you mean, is it a multigraph? So yeah, sure, make it a multigraph. I don't think it will. Yeah, make it a multigraph. And you could have a self loop if h of x equals g of x, for example. OK, so the way that we're going to show this goal is to reason about how the cuckoo graph behaves. It's a random graph because it depends on this hashing. But we want to say some things about this random graph. But before I get to showing this goal, I want to talk about how to get bloomier filters. You can use cuckoo hashing to construct bloomier filters. And bloomier filters are due to Chazelle, Killian, and Rubenfeld, or and Tall. This is from 2004. And they solve the R-bit retrieval problem. Okay. So I mentioned with every element in the set, you want to associate an R-bit string. And when I give you an element in the set, you should output that R-bit string. If I give you something that's not in the set, you can output whatever you want. And we're going to look at the static version. So you know all the items up front, and you just need to create this data structure. And you know the strings as well. So to get bloomier filters, create a cuckoo hash table. Okay. Show that probability there exists a cycle in cuckoo graph is at most a half. Any cycle anywhere in the graph. Show that the probability that happens at most a half. That's something I'm not going to show right now. And if it's the static problem, you know all the items up front. So you'll create the hash table. You'll check, are there any cycles in the cuckoo graph? And if not, you're happy. If so, you'll pick a new hash function. And then keep doing this over and over again until there aren't any cycles. And the expected number of times you have to do this is 2. The expected number of times you have to construct the cuckoo hash table is 2. So you can do that in pre-processing, and you expect to be fast. Suppose there are no cycles now. Then what does the cuckoo graph look like? There are no cycles, so it's a forest. So the graph looks like a forest. Okay. And each one of these edges, what is that edge, right? It's an item, right? Okay. So this is one hash function. This is like g of x or something. So this is some item x. This is like g of x, and that's h of x, or the other way around. And what I'm going to do is I'm going to say x owns its deeper node. Like root all these forests, so that now they have depths. Okay. And let's say that each item owns its deeper node, so x owns this. There's some y here, y owns this. And here's what we're going to do. We're going to fill, at each one of these nodes, we're going to store an R-bit string. At the roots, store 0. At the roots, okay. And then fill in these trees just from top down. And when you get to a node, someone owns that node, namely the person who's written right here. You know what his R-bit value is. And the thing above you has already been filled in, because we're filling in from top down. So fill in this to be whatever it needs to be, so that the XOR of these two is the right thing. Okay. So let me write that down.
The right thing
Being the R-bit string associated with x. So let me write that down. Fill in r-bit strings in forest top down. Every node gets a string. If we query x, we'll output a of g of x XOR a of h of x. That's how we answer queries. And when filling in A, remember every one of these nodes is a memory cell in A. Okay. When filling in A top down, put whatever value in node V is necessary so that querying its owner is correct. Yeah.
Why do we need XOR? Because there are n plus like whatever number plus 1 nodes. So like the number of nodes is more than the number of edges. So you should be sufficient just to store this string just on that one node, right? Like, why are we having XOR?
So the actual memory cells are the vertices, not the edges. So given x, where would you store x's value? Would you store it here or would you store it here? On the deeper node.
There are enough deeper nodes for each one of them.
Oh wait, that's.
Very time to know which one was deeper.
You need to know it anyway.
Yeah, so I guess the point is I really want to use n times r bits. And why can't I? No, what you're saying sounds actually very reasonable.
How do you know which one's deeper in query?
Well, I mean, if this is all static, I can write down for every. Oh, I see.
Well, then you have a one-bit retrieval problem.
Yeah, okay, I see. Right. So how do you know which one is deeper? So you don't actually store the elements. So you can't like have a table that says this element is. Yeah, I see. Yeah, that's a good point. That is a reduction to a one-bit retrieval problem. Huh?
There was a point somewhere over there. I just re-echoed it. So.
Oh, okay. Someone said that over
Yeah,
there?
someone said
Oh, okay. Well, thanks whoever said that.
So I don't want to take the credit.
Yeah, okay. So yes. Yeah, then you need to solve a one-bit retrieval problem. That's a good point. Yeah. Okay. So I guess next time I'll say something about cuckoo hashing, or maybe I'll give it as a homework exercise. I need to decide. I want to wrap up hashing because there are a lot of algorithms out there in the world. Okay, so any questions? Yeah.
So, when we were first talking about k-wise independent,
Yeah.
you showed like those two families that are k-wise independent but not all the way independent.
Like degree k minus 1
Yeah,
polynomials.
yeah,
Yeah.
P or
Yeah.
whatever it is. So, like, are those the ones that are generally used, or how do you come up with new families of k-wise independent?
So there are other actually. Okay, so there are other families of k-wise independent hash functions. One way to get them is by using something called tabulation. So I'll just write a reference. It's a very recent paper. You can look up Thorup in Fox 2013. He shows how to get k-wise. he shows how to construct very fast k-wise independent families using tabulation. Another thing is, if you choose like primes carefully, then some of them, like the mod and division operations, can be bit shifts, and those you can like be very fast with. So one thing that I'll recommend looking at is I forgot all the authors, but Ditzfelbinger and others, and it's called the multiply shift hashing. So he gives some pairwise independent family of hash functions where you never have to do a mod. Everything is just bit shifts. Well, multiplying in bit shifts. Okay. So yeah, but I guess there aren't that many families out there. Actually, it's a very active area of research. In this upcoming, so there's the kind of the biggest theory conferences are Fox and Stock. They each happen once a year. And Fox, Foundations of Computer Science, is happening in October. And one of the papers that's going to appear there this year is some, so k-wise independent polynomials, to evaluate them takes k time, right? Because you have to evaluate this degree k polynomial. So they give k-wise independent families where you can store them efficiently, just like before, using little space, but where evaluation takes constant time, but we're independent of k, but with the caveat that you have to promise me that you're going to evaluate them in order. You're going to compute h of 1, then h of 2, then h of 3, which is not true in a lot of applications, like some of the ones we've been seeing here. But yeah, I mean, getting better hash families is like an open area of research.
Why would the order matter?
I mean, because their running time bounds only hold when, like their algorithm to produce the hash values is only fast when it's sequential.
So does it like memorize something every time you?
I didn't actually read their paper. I just like read the paper. I mean, it hasn't even been presented yet, but it's on the archive, for example. Yeah.